This video is still part on proving limit theorems using the definition. Specifically here, we're talking about the limit of sequences. For this item, we're going to prove that the limit of the difference of the two sequences, a sub n and b sub n, be equal to the difference of their corresponding limits. Here's the statement. Let a sub n and b sub n be convergent sequences of real numbers with the limit of a sub n be identified as L sub 1 and the limit of b sub n is identified as L sub 2. Then the limit of their difference, a sub n minus b sub n, is equal to the limit, the difference of their corresponding limits. Now, to prove statements like this using a definition, we need to structure first, number one, we need to make sure we can express this entire expression as individual limits, okay, as expressions of individual limits, okay, so that we could look into the correct interpretations and connections later on. There are also processes, just like in the previous video where we included triangle inequality, and it's also possible here. We'll be using triangle inequality in order for us to separate those expressions of individual limits. Then we need to look into the proper bounding, or we're going to make some bound on the correct forms so that we could really look into the possibilities of the presence of epsilon. We're talking about epsilon here because the proof of the definition involves certain epsilon. Here's how it goes. Okay, so we are going to let epsilon be greater than 0. Okay, so epsilon is present here. No matter how small it is, it's already identified here. So what we need to do here is we must show that there exists a integer n. Okay, it's an integer such that if this per definition, okay, there exists the definition is natural number k, but we are talking here about integer n. So if n is greater than or equal to that n, okay, then we can write this limit of the difference of two sequences into a absolute value notation. We have here the sequence a sub n minus b sub n minus their limit is less than epsilon. Per definition, this is satisfied. In short, this is our goal. Once we could structure this form, later on showing that this is really less than that said epsilon, then it's already okay per definition. We have proven that this is true. Okay, so how do we look into that? As mentioned, we will start with the possibility of expressing this absolute value notation into the forms of individual limits. Okay, we're talking about individual limits, this aspect here and here. Take note that a limit of a sub n is L sub 1, the limit of b sub n is L sub 2. According to the definition, we need to express it in their form as well. But before we go to that, of course, this, when simplified, I would just like to make sure that a sub n and L sub 1 be paired, b sub n and L sub 2 also be paired. So we can remove our grouping symbols here. Okay, so you will have a sub n minus b sub n. Take note, once you remove the grouping symbol of this, you'll be distributing the negative sign minus L sub 1 plus L sub 2 now. Okay, because that's minus minus. Then you rearrange this to again pair a sub n and L sub 1. So minus L sub 1 minus b sub n, plus L sub 2. Okay, after this, you can have a sub n minus L sub 1. Once you take out negative sign, okay, you have b sub n minus L sub 2. Why is it that we take out negative sign? Because we need to structure this into this form as well to pattern to the definition of the limit. Okay, so just like that. Now, looking into this, in the previous video, if you were not able to view that one, we're talking about the sum of the limits. We simply use automatically the triangle inequality because it is stated that the sum, the absolute value of the sum of two different expressions is just less than or equal to the sum of their individual absolute value notations. Here, it's difference. But we can still invoke the triangle inequality. We have a corollary for that it's still true even when the operation is difference. So this is still, let me change the color to black. Okay. This is still less than or equal to the sum of their individual absolute value notation. Please don't be confused with this. This is not difference because it will really shake our triangle inequality. Still plus, because we have a corollary stating that even if this is minus, we can still express it using triangle inequality under the sum. Okay. Now, we were able to achieve this. As mentioned, this connects to the individual limits. That's the first goal. Now, we can now look into the proper bounds or representations for these two. Okay, so let's have here, since the limit of a sub n is equal to L sub 1 as declared earlier in our statement, then we can look into this form similar, but we cannot use n, or I mean capital letter N, because it's for general. Let's just use there exists n sub 1, which is an integer, such that if n is greater than that n sub 1, okay, then we can now write a sub n minus L sub 1 is less than epsilon as well. Okay, so we can look into this using the definition. However, okay, here's the big thing now. Since we use epsilon here as part of our target goal, we will not be using epsilon here because it would have a problem later on as we look into the epsilon control. We really need to make sure that whatever will be the result of this would be less than epsilon. Okay, so with this now, let's not use epsilon to make it epsilon later on, since there are two of them. So let's use epsilon over 2. Okay, so that is also true here. B sub n is equal to L sub 2. Then there exists, again, we can use capital letter N, and we will use n sub 2, which is an integer, such that if this is such that n is greater than or equal to n sub 2, then the absolute value, sorry, this is B, my bad, B sub n minus L sub 2 is less than still epsilon over 2. Okay, this is unique to this form. We cannot use epsilon over 2 all the time. We used that in the previous video for the sum. We'll be using that again here in difference, but it's not all the time epsilon over 2 for all limit theorems, because you really need to look into the proper forms of your bound so that you will return to your epsilon as targeted here. Okay, so after that, since we are looking for n, there exists n, not n sub 1 and n sub 2. So let's also make some descriptions on our n. Take n be the maximum of your n sub 1 and n sub 2. Why do we use maximum? Make sure you need to write yourselves rather with the definition that n is greater than n sub 1 and n sub 2, and also n is greater than n here. Meaning, to make sure that this fits the definition, let's take the maximum, not the minimum. Because whatever will be the maximum, whether it's n sub 1 or n sub 2, and you're picking that, and n is still greater than that maximum, then definitely you are still on the right track. Because the next statement here is this: if n is greater than or equal to your n. So, no matter how large is this, if n is still greater than that, okay, depending on what is the maximum, that's why we pick the maximum, we are still on the definition. So, we have this, we can now state a sub n minus b sub n, going now to our intended output, L sub 1 minus L sub 2, to which we're able to use our form a sub n here. I'm not going to copy this. So from here, I'm going to jump here immediately. Not that one, sorry. This one here, where we already grouped them into their corresponding limits. So minus L sub 1, but this time this is minus B sub n minus L sub 2. Okay? And again, according to triangle inequality, this is less than or equal to the sum of their individual expressions. Okay, sum. Don't be confused again with that. I made some points on that. Okay, so once we use this during triangle inequality, take note, we have specified that the absolute value of a sub n minus L sub 1 is less than epsilon over 2. Also true here. So we can now say that this is still less than epsilon over 2 plus epsilon over 2. When we add it, it's epsilon. Look into this, just simply this part here and this part here. Okay, so we have shown that the absolute value of a sub n minus b sub n minus L sub 1 minus L sub 2, let me remove this, okay, is less than epsilon. And this is actually what was our goal earlier. So it's also important for you to note what do you want to show, that you will be guided later on. Once we have shown this, then we cannot invoke this as true. Okay, so finally, okay, so we have, since epsilon greater than 0 is arbitrary, then we conclude that the limit of the difference, this is one of the limit theorems, but this time is difference, the previous video it's sum, is equal to the difference of their corresponding limits. And that is the end of the proof, because we were able to establish this part here. So please try to review these steps here, as you will be guided on how to show this proof by yourself. Thank you very much for watching.